Welcome to the energies of solution formation. So, solubility is important in biological systems because it determines whether a toxin is dangerous to an organism or not. So, for example, DDT, which is a mosquito pesticide, is unsafe for humans because it's only slightly soluble in water, but it's quite soluble in fat. And this means that DDT accumulates in fat deposits in the body. Because when you have a small amount of DDT that's able to dissolve in the blood, an aqueous solution, you get very low concentrations of DDT in the blood, but that means that the DDT is able to move throughout the body, and when it reaches a fat deposit, it's more soluble in the fat, so it moves from the blood into the fat, and now it stays there. It's much less likely to move out of the fat back into the blood, because it's significantly less soluble in the blood. And that means that over time, DDT accumulates in the fat deposits in your body, and it can build up to dangerous levels and cause problems in your body. So, similarly, mercury can enter the bloodstream via the lungs. It's only slightly soluble in water, but it's very soluble in fats, which means that mercury accumulates in the fat deposits in your body just like the DDT does. And this is not a problem in most places in your body, but it's a very big problem in the brain, because in the axons around the axons of neurons in your brain, there are fat deposits, and this means that the mercury accumulates in those fat deposits, and it's able to interfere with the electrical impulses traveling through the neuron. Now, if the mercury is interfering with the impulses traveling through the neurons in your brain, that means that your neurons aren't working correctly. That basically means your brain is not working correctly. That means that you end up going crazy. So, a few hundred years ago, hatters used mercury in certain dyes, and this constant exposure to lead led to the term Mad Hatter, because many of them went crazy because of this lifelong exposure to the mercury. And this is, of course, why we try to eliminate mercury from most of the things that we use now. Thermometers, which used to contain mercury as the volume changing ingredient, now we use usually, well, either it's a digital thermometer, which is what is often used in homes or in scientific laboratories. Now we use an alcohol-based substance instead of the mercury. So, what affects solubility? Well, a general rule of thumb is like dissolves like. So, polar solutes dissolve well in polar solvents, and nonpolar solutes dissolve well in nonpolar solvents. So, like dissolves like. If the polarity of your solute and your solvent are alike, then the solubility is likely to be fairly high. If the polarities are very different, then the solubility is likely to be very low. So let's assume that the dissolution process requires 3 steps. First step is separating the solute into its individual components, which means expanding the solute. So you have some either molecules bound in a lattice structure, let's say. You need to separate those molecules from one another, so you're breaking those intermolecular forces. Or you have some ions that are bound together into an ionic lattice structure, and again, you still have to separate those inter-ionic forces and break each cation away from the anions that surround it, and break each of the anions around from the cations that surround it. So that's step 1. So the second step is separating the solvent into its individual components, so expanding the solvent. So in the solvent, there are some intermolecular forces. So if you have, say, water, you have to separate those water molecules by a little bit in order to get an ion, cation, or anion, or the solute molecule dissolved in between. So you're still separating some of those. You're breaking some of the solvent intermolecular forces. You're breaking most of the solute intermolecular forces. Then the third step is to bring together the solute and the solvent in the mixing process, and you're forming some solute-solvent intermolecular forces. So separating the solute into its individual components was the first step. So this process requires energy to break those intermolecular or interionic forces holding our molecules or ions into the solid. So we have to put energy for this first step. The second step was separating the solvent into its individual components, so expanding our solvent. Again, this process requires energy to break the intermolecular forces holding our solvent molecules together. And the third step was bringing together the solute and the solvent, the mixing process. This process releases energy as the intermolecular forces are formed between the solute and the solvent. So we can show this sort of graphically. We start out here with our solute. We have to, in step one, break them apart, break those molecules apart, or ions. In step two, we have our solvent. We need to separate our solvent molecules from one another. And then step three is the mixing of our now expanded solute and solvent together into the solution. Now remember that Hense's law says that we can perform this in one step, separate our solute, solvent, and mix them together all in one step to give us our solution. Or we can do this in three separate steps. Separate the solute, separate the solvent, then mix them together, and the energy change is the same for each process. The overall energy change is the same for whether we do it in one step or whether we do it in three steps. So, the enthalpy of solution, or the heat of solution, this delta H solution, is the enthalpy change associated with the formation of a solution. So when we go from our separated solute and our separated our separated solute and solvent, not by separated, I don't mean expanded, in this case I mean the pure solute and solvent, to the solution where we've got them mixed. So the enthalpy of solution is the sum of the enthalpy changes for each of the three steps that we showed above. The separating of the solute, the separating of the expanding of the solute, the expanding of the solvent, and the mixing process. Right? That's all, the sum of those three is the enthalpy change for solution. So, the enthalpy of solution may be positive, which means energy is being absorbed, or it may be negative, which means energy is being released. So, the enthalpy of solution is positive if that mixing enthalpy is larger, more positive, than the sum of the first and second process, the expanding of our soluted solvent, which basically means if it takes more energy to expand our solute and solvent than we get back by mixing and forming those intermolecular forces. Remember, forming bonds gives us energy, breaking bonds requires inputting energy. So if we get out less energy than what we put in, then our enthalpy of solution will be positive. If the energy that's released is less than the sum of the energies, the energy that we have to put in, then the enthalpy of solution will be negative. So let's examine the dissolution of sodium chloride in water. So step one involves separating the sodium ions from the chloride ions. This requires inputting a good deal of energy to break the bonds between the ions. Step two involves separating the water molecules from one another. This involves, again, inputting energy to break some of the intermolecular forces between the water molecules. We don't have to break all of the intermolecular forces between the water molecules, just some of them. Because we don't have to totally separate the water molecules from one another. We just have to separate them enough to be able to fit the sodium and chloride ions in between. So then step three involves mixing the sodium ions, chloride ions, and water molecules together. And as the ions become hydrated, which again means the surrounding by the water molecules, they're surrounded by the solvent, the intermolecular forces form between the ions and the water molecules, and this releases energy. So, because step three involves forming ion-dipole intermolecular forces, there's more energy released in step three. So that's this step here, going from here down to there. So here's where we start out with our separated solute and solvent, pure solute, pure solvent. When we expand them, we go up to here, and then when we mix them, we go down to there. So overall, we're going from this level, that energy, down to this energy. Our enthalpy change will be negative because we're releasing energy. We're releasing more energy than what we had to put in. So overall, we get energy out. So Again, because we're forming these very strong ion-dipole intermolecular forces, there's a lot more energy that's released here than the energy that we had to put in to separate our pure substances. And that means that the enthalpy of solution is positive. So let's examine the dissolution of oil in water. So step one involves separating the oil molecules from one another, and this requires inputting energy to break the bonds between the molecules, between the oil molecules. And this will require less energy than separating the sodium chloride, but still a fair amount of energy because the oil molecules are large and thus have significant dispersion forces. So step two involves separating the water molecules from one another. This requires inputting energy to break some of the intermolecular forces between the water molecules. And this will require a fair amount of energy because the water molecules exhibit hydrogen bonding. This will be roughly the same value as for the last example, because we're still separating the water molecules by about the same amount. Step three involves mixing the oil molecules and the water molecules. Now, as the oil and water molecules mix, they form intermolecular bonds, releasing energy. But this releases only a small amount of energy because the water and oil molecules only have dispersion forces bonding them together. Because the oil is nonpolar, the water is very polar. Because the oil is nonpolar, it doesn't have any dipole forces. So all it has is the London dispersion forces. So the oil and water are only held together by the London dispersion forces. And that means that we're not going to get very much energy out. And that means that when we put in some amount of energy to break our pure substances apart, to break some of those intermolecular bonds, when we get back some energy, when we release some energy by forming those water-oil intermolecular bonds, we don't get out as much as what we had to put in. And that means that now the enthalpy of solution, we're going to have to put in energy, and the enthalpy of solution is negative there. So that was the energies of solution formation.